This is 9B problems, number 42. We're going to start off 42, 46. Stop at 50 and do part 2 then for 50, 60, and 78. So 42A, draw a Lewis structure for silane. Silane is SiH4 and predict its molecular geometry. Well, this is actually much easier than you would think it would be. Silane is very similar to methane. Methane is CH4. Notice that both carbon and silicon, when we're doing these problems, you should have some kind of periodic table out in front so you can see where they are. Because placement of these elements in the periodic table essentially tells you how they relate to each other. And when I say something like methane, that means that methane and silane are going to behave or have very similar geometry. So if I count going from left to right on the periodic table, hydrogen, beryllium, boron, carbon. Carbon is the fourth. If I skip over the transition metals, carbon's the fourth one. And silicon is in that group, so that means that for the Lewis structure, there we go, silicon is going to have a dot diagram that looks like this. There are 4 valence electrons. We space them out, one on each side of the imaginary box around silicon. Hydrogen, of course, has only one because it's in the first group, and that looks like that. Notice that if I have 4 hydrogens, that matches up perfectly with the 4 dots that I have around silicon. So it's going to end up looking like this. Now, this is not a depiction of what it looks like because this is a 3D molecule on a 2-dimensional surface, so it doesn't look like this with 90-degree bond angles. Actually, once we have this down, we can look at our charts that we have for 9.2. We have 1, 2, 3, 4 electron domains. 4 electron domains means that I have tetrahedral. If I have, that's my electron domain geometry. If I have no non-bonding, so if it's 4 bonds and 0 non-bonding, then tetrahedral then is also my molecular geometry. Okay? So molecular geometry is tetrahedral, electron domain geometry is tetrahedral. That means we have bond angles of 109.5. This, of course, says, like, once we get through this stuff, predict its molecular geometry. Did that. Is it necessary to promote an electron before forming hybrid orbitals for the Si atom? Yes, it is. How do I know that? Well, let's take a look at the valence electron structure for silane. Silane for silicon is neon, 3s2, 3p2. Okay, so we have 3s2, 3p2 as the valence electrons. There are 4 of them. That means that as far as 3s, I have one of these. That's I knew it was going to do that. There's my orbital for 3s. It looks like this. My 3p has 3 orbitals like this, and there's 2 in there. So what happens? One of these jumps up here like this. So now that we have 1 per orbital, which means that silicon can now, instead of combining to form 2 bonds with 2 single electrons, now it can form 3 if we hybridize the S and the P. So what does that mean? Well, that means that after I hybridize, it looks like this. I have 1s and 3p that have now electrons in them waiting to bond with the electron from hydrogen in each of the orbitals. Okay, so it had to promote 1 electron up to the s up to the empty 3p orbital. Okay, so this is what hybridization looks like. This is what happens when you promote an electron. This right here is how we promote. That's what it says, promote there. So just take my word for that. So there are not 5 electrons. There is 1 electron right here that is moving up to an empty orbital because it's more stable that way. So that's my answer for that. Is it necessary to promote an electron? The answer is yes, and this is how it works. What type of hybridization exists in SiH4? Well, it doesn't matter I know I just showed you this. So you would say it is sp3, but what you can do is you can just remember that anytime you have tetrahedral for electron domain, that sp3 is what you have. It doesn't matter whether it's one of those situations where, remember oxygen looks like this, but because we have the two lone pairs here and here, that's tetrahedral. It's tetrahedral. This is water. I have 1, 2, 3, 4. That's what makes it tetrahedral. And because it's 4 like that, it doesn't matter how many lone pairs there are or bonds there are. It's going to be sp3 no matter what. And the S and the P should be the same size. sp3 like that. Yep. sp3 means that we have 1 s orbital and 3 p orbitals that are being filled or bonded. And that's all it means, sp3. Okay, so type of hybridization is sp3. It has to be for any tetrahedral electron domain. In one diagram, sketch 2 of the 2 electron bonds formed when Si and H1s orbital. How would the other SiH bonds be oriented relative to your sketch? Well, it would look something a little bit like this. Here's the p orbital here, here's the s orbital. When we put them together, we get a big lobe and a small lobe. That's one sp orbital. Okay, when we put them together, then we see something that looks like this. So here's one orbital, here's another orbital. We put them together. Ow, I have an itch. Now, so here is our H with our 1s orbital, and then over here is going to be some of the, like that. And then the other one, this would be, okay. Now we have 4 that we have to account for. So 2 of them are going to look like this. Like that. And then we have the overlap there for the 1s for the H. This is all silicon right here. Okay, that's 2 of them. The reason why I drew it like this is because this should have a bond angle of 109.5 degrees. Okay, 109.5. Another one would then go off in a different direction, kind of like that, and then the 4th one would go off in a different direction, but it would be, of course you guys know that none of this is 2-dimensional, that this is a 3-dimensional thing, so the bond angles don't translate very well on a 2-dimensional surface. So let's go back here. There's my picture for what it looks like. Notice I have a small lobe right here. Sorry. I have the small lobe right here and the larger lobe right here when we combine an S and a P. Now this is just a straight up 1s over here for hydrogen. So this 1s like this is going to overlap with its 1 electron, and we end up with 2 electrons in between the 2 of them there. Okay, so let's keep going. 46A, starting with an orbital diagram of sulfur atom, describe what steps are needed to construct the hybrid orbitals appropriate to describe the bonding in SF2. Okay, well this isn't too bad. First of all, for sulfur, we have neon, like this, 3s2, 3p4, like that. So when I draw an orbital diagram of 3s2, I get this. Of 3p4, I get like that. That means that I have spots here and here to bond with my F. So my F, like this, has 1 goes here, and 1 goes there, like that. So now this still all like hybridizes to sp3 because we have 4 places where we have it. It really does come down to this. If I'm going to draw the Lewis structure for SF, it would look something like this. I would count 1, 2, 3, 4. That would give me tetrahedral. Okay, tetrahedral means sp3 hybridization. Okay, that means that these two here, the S and the P, would combine to form 1s and 3p. Like this. And then the extra ones would come from fluorine, like that. Okay, so sp3. So it's always, if it's tetrahedral, it's always sp3. If it's trigonal bipyramidal, it's always sp3d, which is something else we're going to get into. What is the name given to the hybrid orbitals constructed in A? I just answered that. sp3. That's the name of the hybrid orbitals. Moving on. In one origin, sketch the large lobes of the hydrogen of the hybrid orbitals constructed in A. We did this before. I think I have a picture of it. Does it look like? Yep, there it is. So this is what it looks like in tetrahedral. I tried to draw this for 42 with that like that, and then the other one would be overlapping like that, and another one would be overlapping like that, and then finally the last one. Obviously I screwed that up so badly it's almost not recognizable. But this would be like if I took, it's asking for the first two, so if I took these two and overlapped them on themselves, it would look like small lobe, big lobe, like that. And that would be what it should look like there. Let me go back to D, okay? So I can't do this very well. There's one SP, the other one, I don't know. Well, that looks like some kind of ridiculous ribbon. Okay, whatever. Would the hybridization scheme in part A be appropriate for SF4? Explain. Of course not. So what's happening in SF4? Well, in SF4, we start off like this. We see that we can bond two of the F's like that, but then what I have to do then is break up these two paired and bond two like that. That means now I have 1, 2, 3, 4, 5 electron domains. Okay, 5 electron domains is trigonal bipyramidal. Okay, so 5 electron domains is trigonal bipyramidal. Now, what's going on with trigonal bipyramidal? I thought we ran out. Remember, sulfur still has this. I know this is like, you guys are all like, whoa, what's he talking about? Check this out. I still have this. Okay. So what happens then is way over here, after the 4s, what is this with 5? Okay, and no electrons. This is, of course, is the 3D. We've talked about this. Expanded octets happen because there's extra room in the 3D, which means that now this one is promoted from the 3P to the 3D, and now look what happens. When I get rid of, okay, hang on, I'm going to have to rewrite this. So when I move, that one electron is promoted here, notice that it's got room here, 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 and here. All 5 of these orbitals end up being together. Let me show you what it looks like. So what happens here is, I'm going to do this all in green just to keep it constant here, is that I got S, P, and 1D, all like this. This is sp3d. Okay, the 3 for the P comes from 1, 2, 3 orbitals that are P, and there's only one that's D, and there's only one that's S. And that's why the S and the D don't have numbers. And then what's left over then? Well, I'll do this in a different color just to make it look Notice now the 3D has 4 orbitals instead of 5, because one of the 5 orbitals has been degenerized. I think I just made up a new word, which means that they're all now, the D has become part, that 1D orbital with an electron in it, this one right here, this one has now been like pulled down and integrated with the other 4. So now I have 5 orbitals that are called degenerate, which means all at the same energy, which is where sp3d comes from. And that's only with a trigonal bipyramidal. Okay, so this is not the same. Definitely not the same. And that's 50, and that's part 2 of 9B problems.